So when we were looking at buffers before, we saw that we can calculate the pH using an ice table. I used my ice table to determine the concentration of the H+, and from there, the negative log of the H+ concentration equals pH. Alternately, I can use something called the Henderson-Hasselbalch equation. Now, the Henderson-Hasselbalch equation says that for a buffer, the pH is going to be equal to the pKa plus the log of the concentration of our base over the concentration of our acid. Now, just like the pH is the negative log of the H+ concentration, our pKa is the negative log of our Ka. Now, because the pH is going to be equal to the pKa, remember our Ka is a constant, plus the log of the concentration of our base over our acid. If we have the same ratio of our acid to our base, we will have the same pH. So a buffer that's made of 5 molar acetic acid and 3 molar sodium acetate will have the same pH as a buffer made from 0.05 molar acetic acid and 0.03 molar sodium acetate. Because our ratio stays the same, our pH stays the same. Okay? So here's the way we actually use the Henderson-Hasselbalch equation to calculate pH. So I'm told that I've got 0.75 molar lactic acid, they give me the Ka, and 0.25 molar sodium lactate. So I know that the Henderson-Hasselbalch equation is the pH is equal to the negative log of my Ka. My Ka is 1.4 times 10 to the negative 4th, plus the log of the concentration of my base. My base is going to be the sodium lactate, the CH3H5O3 minus, so that's 0.25 molar, over the concentration of my acid, which is 0.75 molar. So when I plug this into my calculator, I get the pH is equal to 3.85 plus, this is going to come out to be negative 0.48. So when I calculate my pH, the pH is going to be 3.37. No ice table, not a lot of work, no problem. Okay? Now I can still use the Henderson-Hasselbalch equation if I'm given the Kb. Now it's important to remember that Ka times Kb is always equal to Kw. And Kw is a constant. It's 1.0 times 10 to the negative 14th. So take a second to solve example 7. They give you 0.25 molar NH3, which is our base. So they give you the Kb. They tell you you have 0.40 molar NH4Cl, and they ask you to calculate the pH of the solution. So the first thing you'll need to do, change your Kb to a Ka using that equation. Once you have your Ka, use the Henderson-Hasselbalch equation. The pH equals the negative log of the Ka plus the log of the concentration of your base, which was NH3, over the concentration of your acid, which is NH4. So remember, buffers are going to have large concentrations of a weak acid and its conjugate weak base. I can either have the weak acid and the conjugate base, or a weak base and the conjugate weak acid, but I have to have both parts. If I add an acid to a solution, the acid is going to react with the base in solution. If I add base to my buffer, the base is going to react with the acid in solution. That's why I need to have both parts. I can't have just one, I have to have both in order to resist the change in the pH. Okay? The other thing to remember is that the pH of my buffer is determined by the ratio of my weak acid to my weak base. So it doesn't matter the magnitude, just the ratio. Okay? So when we talk about buffers, we can talk about buffering capacity. The buffering capacity is the amount of H plus or OH minus that the buffer can absorb without changing the pH significantly. Think of buffering capacity as how good or how strong a buffer is. The higher the buffering capacity, the more acid or base I can absorb, the more it resists the change in pH. Okay? Now we already said that the pH of a buffered solution was determined by the ratio of A minus to HA, or my base to my acid. How good my buffer is determined by the magnitude of the HA to the A minus, the acid to the base. Okay? So here's what I mean by magnitude. So we've got two different solutions. I want to calculate the change in pH that occurs when 0.1 molar HCl is added to 1 liter of each of the following solutions. Okay? So since I'm calculating the change in pH, I need to know my initial pH. So I'm going to look at solution A. So for solution A, pH equals the negative log of the Ka. For acetic acid, the Ka is 1.8 times 10 to the negative fifth, plus the concentration of my, plus the log of the concentration of my acid. Acetic acid is 5, over the concentration of my base, which is also 5. So these are going to cancel out to form 1. Well, it turns out the log of 1 is 0. So my pH is equal to the negative log of 1.8 times 10 to the negative 5. So my pH initially is 4.74. Now I'm going to add some HCl. So I have acetic acid. I know it's going to form H plus and the acetate ion. I know that initially I have 5 molar acetic acid. Initially I have 5 molar sodium acetate. I'm adding 0.010 molar HCl. Now, because HCl is an acid, it is going to get rid of my base. It will neutralize my base, so that's going to go away. So this forms 4.99. My acid is going to reform, so I'm going to add those two. So I get 5.01. Remember, an acid neutralizes a base, so I'm adding more H plus. This reacts, goes that way. Okay? So now, to determine the change in pH, remember, my pH was equal to the negative log of 1.8 times 10 to the negative fifth. That didn't change. Plus the log of my base, 4.99, over the log of my acid. So this is going to be negative 0.0017. So the pH of my acid is going to change from 4.74. It's going to go down by 0.0017. The pH really doesn't change hardly at all. It's going to change to 4.738. It hardly moves at all. Okay? So take a second and solve for solution B. You know that the solution this time is 0.05 molar C2H3O2, and it's 0.05 molar sodium acetate. Now, because the ratio is still the same, my initial pH is still the same, you are solving for the change just like I did.